As winter tightens its grip, a small amphibian slowly freezes. Ice fills its body, its heart stops, and breathing ceases. Yet when spring returns, this animal awakens and continues its life. In the forests of North America, winter temperatures often fall far below freezing. Most amphibians survive these conditions by retreating beneath the frost line in ponds or underground shelters. One species, however, endures winter in a far more extraordinary way. The wood frog, Rana sylvatica, spends winter frozen solid. This small brown frog inhabits boreal forests, wetlands, and tundra environments across a vast geographic range extending from the northeastern United States through Canada and into Alaska. In these regions, winter temperatures may fall below -30 degrees Celsius -22 degrees Fahrenheit. Unlike aquatic frogs that overwinter at the bottom of lakes, wood frogs often remain in shallow leaf litter on the forest floor. As temperatures drop in autumn, the frog buries itself beneath leaves and soil where snow will eventually accumulate. When freezing temperatures arrive, ice crystals begin forming within the frog's body. Within hours, up to 65 to 70% of the water inside its tissues can freeze. Under ordinary biological conditions, such freezing would destroy cells and cause immediate death. Ice expands as it forms, rupturing membranes and disrupting internal structures. Yet the wood frog survives. During the frozen state, the frog's heart stops beating, its lungs cease functioning, and blood circulation halts entirely. Metabolism drops to nearly undetectable levels. For weeks, sometimes months, the frog exists in a state that closely resembles death. And when temperatures rise in spring, it thaws and resumes normal activity. The survival of freezing temperatures depends on a remarkable biochemical defense system. As soon as ice begins forming in the frog's body, specialized sensors trigger rapid metabolic changes. The frog's liver releases massive quantities of glucose into the bloodstream. Glucose acts as a cryoprotectant, a compound that helps protect cells from damage during freezing. Within minutes, glucose concentrations in the frog's tissues can increase up to 100 times higher than normal levels. This rapid surge distributes throughout the body, entering cells and stabilizing their internal structures. In addition to glucose, wood frogs accumulate urea, another compound that contributes to freezing tolerance by balancing osmotic pressure and reducing cellular dehydration. These chemicals function similarly to antifreeze in mechanical systems. They lower the freezing point of intracellular fluids and reduce the formation of damaging ice crystals inside cells. Importantly, ice does not form uniformly throughout the frog's body. Freezing begins in the extracellular spaces, the fluid surrounding cells, while the interior of many cells remains protected by high concentrations of glucose. This controlled pattern of freezing prevents catastrophic structural damage. The frog's physiology transforms a lethal process into a reversible state of suspended life. The freezing process itself is highly regulated. Wood frogs rely on external ice crystals, often present in surrounding soil or leaf litter, to initiate freezing in their bodies. This process is known as ice nucleation. Once nucleation begins, ice spreads gradually through the frog's extracellular fluids. As ice forms, water is drawn out of the cells by osmotic pressure. The cells shrink but remain intact because the cryoprotectants stabilize their membranes. During this stage, the frog's organs progressively shut down. Within minutes, the heart stops beating. Blood no longer circulates. Neural activity in the brain falls to extremely low levels. Yet the cells themselves remain structurally intact. The frozen frog may appear lifeless. Its body becomes rigid, and ice crystals may even form beneath the skin. However, deep within its tissues, biochemical systems preserve the integrity of vital organs. This state of suspended animation can persist for 8 months or more in northern regions. The return of warmer temperatures reverses the process. When spring sunlight warms the forest floor, the thawing process begins. Ice crystals slowly melt, and water re-enters the cells. Blood circulation resumes as the heart gradually restarts. Within several hours, metabolic activity returns to normal levels. One of the most remarkable aspects of this recovery is the restoration of neurological function. Despite months without oxygen circulation to the brain, wood frogs typically show no lasting neurological damage after thawing. Researchers believe that extremely low metabolic rates during freezing reduce the energy demands of neurons, preventing the damage that would normally occur during oxygen deprivation. Within 24 hours, a fully thawed frog may begin moving again. Soon afterward, it migrates toward temporary spring pools to begin the breeding season. This rapid transition from frozen dormancy to active reproduction allows wood frogs to take advantage of seasonal habitats before predators and competitors arrive. The freezing survival strategy of the wood frog has attracted significant scientific interest. Understanding how this amphibian protects its cells from freezing damage may help researchers develop new methods for cryopreservation, the preservation of biological tissues at extremely low temperatures. Cryopreservation is already used in medicine to store blood cells, reproductive cells, and certain tissues. However, freezing entire organs for transplantation remains extremely difficult because ice formation damages cellular structures. Wood frogs demonstrate that large amounts of tissue can survive freezing if the process is carefully controlled and supported by protective compounds. Scientists are studying how glucose, urea, and other cryoprotectants stabilize membranes and proteins during freezing. Insights from these mechanisms may one day improve long-term storage of organs for transplantation or preservation of endangered species. The frog's natural adaptation represents a powerful example of how evolution solves complex biological challenges. In extreme environments, survival often depends on solutions that appear almost impossible from a human perspective. The distribution of wood frogs extends farther north than any other amphibian species in North America. Populations occur well within the Arctic Circle, where winters are long and severe. Few amphibians could survive such conditions without specialized physiological adaptations. The wood frog's freezing tolerance allows it to remain in terrestrial habitats rather than depending on deep water bodies for winter refuge. This flexibility expands the environments it can occupy. However, survival still depends on precise environmental timing. Snow cover plays an important role by insulating the forest floor. A thick layer of snow helps prevent temperatures in the leaf litter from dropping to levels that would cause irreversible damage. Without this insulation, extreme cold could exceed the frog's tolerance limits. This delicate balance between physiology and environment illustrates how finely tuned evolutionary adaptations can be. The wood frog's ability to freeze and revive is not merely a biological curiosity. It is a carefully evolved survival strategy shaped by thousands of generations living in harsh northern climates. Thank you for watching. Subscribe for more journeys into the remarkable strategies animals use to survive on Earth, where even a frozen heart can begin beating again with the return of spring.